Good morning, everybody. I missed some of you in the office hours today, and I went over a little bit of the content that we are going to discuss in the chapter today. So a brief review of what was covered basically in part 1 of chapter 6 is we worked on in the last chapter, in the same chapter, part 1, we worked on the work done by constant force, and we worked on some of the formulas related to work done and did some problems in the PowerPoint. Hope you are checking the work and looking at the videos. We also worked on kinetic energy and work energy principle. We basically showed that how work is done when there's change in kinetic energy, which is obvious. If an object is moving and has kinetic energy, then work will be done. And work done can be positive or negative. If an object is slowing down, then work done is negative when an object slows down, and a work done will be positive. These are the shortcut symbols I'm writing for positive and negative. Work done is positive when it is accelerating, or when it accelerates or goes faster. So know these differences, and we ended our lecture last time at change in gravitational potential energy, and saying that there are two different types of potential energies. One is PEG and one is PE due to the elasticity of the objects, like for example elastic springs or a rubber band, or anything that has elasticity like bungee cord. So all those objects which can exhibit elastic properties will have potential energy due to the elasticity of the object. All right. So let us now go ahead and discuss elastic potential energy. And a potential energy can also be stored in the spring when it is compressed. So you played with toys when you were little, and you know that compressed spring can launch many things, rockets, and or as simple toys like these found in Chuck E. Cheese. If you've been to Chuck E. Cheese, I'm sure you have. So if it's at rest, this is the equilibrium position. And in equilibrium means there is no stretching happening. So when you compress it, you're compressing it by some distance. The original distance is this much, but you compressed it in this way, so that distance of compression is taken as delta x, and then it is launched, or it can do the work. The compressed spring has stored potential energy. So compressed spring has stored potential energy, and it's called elastic potential energy. When released, that energy gets converted to kinetic energy. So you again see there is a transfer of energy from potential to kinetic, or vice versa can also happen. If a ball is thrown on the spring and is directed this way on the spring will compress a little. So kinetic energy has been converted into elastic potential energy. So vice versa is possible. So there's basically a rule that we set first. There was a famous scientist called Hooke, and the name also goes for the law he gave, Hooke's law. Hooke's law basically relates to springs. Here he said that if a spring, he experimented and he found that if several weights were suspended on the spring and it stretched by several distances, so he saw that if he kept on increasing these weights, the distance with which it stretched increased. So that is why it was said that force of the spring is directly proportional to x. Now you must be wondering, why is this minus here? This is minus because when the spring is in the equilibrium position, no forces are acting on it, you're not pulling or it's not compressing. But next you applied a force, to an external force, you are pulling it, but the spring is trying to get back to its original position. So spring force is in the opposite force of the force exerted, or the external force. So they act in opposite direction, and hence you have a minus sign here. So you see that the force is in this way, the distance is getting stretched this way. So there's the angle between the two is 180 degrees. Hence, it becomes minus kx. So force is directly proportional to displacement. You stretch it, the distance will increase, but the spring force is acting in the opposite direction. So now you must be wondering, what is this k? So this k is not kilo, it is not 10 raised power 3. When a proportionality sign is removed, then we put an equality sign here, and that equality was replaced by a constant. And this is a constant for a certain type of a spring. Every spring has its own value of k. So spring constant, that's why it's called a constant. If I have a spring of a certain rigidity, it represents the rigidness of a spring. Springs that are harder will have higher values of k, and springs that are softer will have lower values of k. Unfortunately, we were going to do this lab, and this was the lab that was meant for our for your lab report. And this was a very good lab where you were going to suspend several weights, measure the distance with which it is going to come down, and then plot a graph and then write a lab report. But since we cannot do that anymore, I will have you do something else for the lab report, an alternate assignment or something like that on the PhET, and let's see how it goes. I have not still put thought into that, but it will be simpler, it won't be something confusing. So when it was found by Hooke that when he applied different forces, and he plotted a graph between different forces applied and different displacements happening, he found that there was a direct relationship, and when he plotted, we got a straight line. You know that force on the y-axis and x on the x-axis is the displacement. This is what you would have done for your graph in Data Studio. And then he found out what is the work done. It's a beautiful expression. Basically, it shows that when a constant force is applied, since we are only dealing with constant forces, the work done, now in our case it's the work done here is the work done by the spring, or work done by the elastic component that you've used. Work done is force times distance, right? So, or work done is given by the area under the graph. For this kind of scenario, the area under the graph is given by this. It's just like the slope of the line. The slope of the line is rise by run, and the rise is given by the area of this triangle. Area of a triangle is half of base, which is x, multiplied by height. So that becomes area of the triangle is half of x, which is your base, multiplied by force due to the spring. Okay, now force due to the spring, the magnitude of the force, I'll say that the external force that you're applying is the with which the weights were getting pulled is the weight Fg, but it is equivalent to k into x. We learned that force due to the spring is equivalent to minus force due to the external, that is the pull or push that you exerted. So therefore your external force, this was minus, so that becomes 1 by 2 x into 1 by 2x times k into x, because that's what the external force is equivalent to. Minus times minus of f of s will give plus kx. So overall, the area comes out to be 1 by 2 kx square. And this is the work done by the spring. If I stretch the spring, it does this much work. And we use the formula work done is equivalent to force multiplied by distance. Here, the distance or the displacement is x. It is in a direction opposite to that of the displacement happens in a direction opposite to the spring force, but it happens in the same direction as the external force. So we can put a positive sign. So 1 by 2 kx square, or in short, we write potential energy is equivalent to 1 by 2 x square, which is also equivalent to work done. Again, just like we say that work done is equivalent to kinetic energy change, here also work done is equal to change in potential energy due to the elastic stretching or compressing of the spring. So how about working on a problem here now? We have a spring with a constant given. Different values for springs are given. So let us see what are the given quantities for this problem. Your K is given as 88.0 newtons per meter. By the way, I forgot to mention why we have Newton per meter for the spring constant. Spring force is equivalent to minus force due to the external force is equivalent to minus K of x. Force is measured in Newton. How will we measure K then? X is measured in meters. So if I have to find K, so for example, if I have to find K, divide both sides by, if I take Fs is equivalent to minus Kx, or you can also say minus external force is equivalent to minus Kx. You can cancel this sign. Either one is fine. You can use the magnitude. Both are equal but opposite. So K, divide both sides by K, you get F of external divided by K will be equivalent to, divided by X is equivalent to K. Divide both sides by X. The unit of force is Newton. The unit of X is meter. Hence the unit of K in SI system will be newtons per meter. Okay, so that should have been part of the previous slide, but now you know why K is Newton per meter. So I'll go ahead and erase this and we'll get started with the problem. So the spring constant is given, and we have been given work done. If you look at the units, 45 joules. So how much must the spring be compressed to store a 45 joules of potential energy? So potential energy is given, and it is equivalent to 45.0 joules. We also know that potential energy formula is 1 by 2k x square. So we have all the values, we have the formula. We can have a spring scenario. So if I have a spring, initially it was not compressed, it was in its normal position, no stretching or compressing, but then I compressed it, so I must have used the external force, and it compressed by a distance x, right? You have to find out how much the spring must be compressed, so you have to find x. So again, we will use the formula. The magnitude of the potential energy is given, which is the work done, 1 by 2k x squared. So PE is 45.0 joules. You know that the unit of work is always joule or energy. K is given as 88.0. You can find your x square. So work on the mathematical steps here. Multiply both sides by 2. 2 multiplied by 45.0 is, so the 2 on this side gets cancelled. You have 88.0 still there. Divide both sides by 88. So in the next step, you have 2 multiplied by 45.0 divided by 88.0 is equivalent to x squared. So go ahead and find out your x. Your x will be square root of 2 multiplied by 45.0 whole divided by 88.0. And once you solve this, you should be able to find out the value of your x is equivalent to 1. It compresses by nearly a meter, 1.01 meters. Make sure all units are in SI system. That's how you, with the help of energy, you can solve this problem. But this time we are not working on gravitational potential energy. We're working on elastic potential energy. Similarly, we can work on another problem, which is a 1200 kg car moving on a horizontal surface. These are all your textbook problems, so it's good that you can go and revisit them. There's a 1200 kg car moving on a horizontal surface, has a speed of 85 kilometers per hour when it strikes a horizontal coiled spring and is brought to rest. So these are important things you should always underline, which seems important, in a distance of 2.2 meters. So in the previous problem, you saw how a spring has compressed energy and it can do the work and it sets it into motion. But here we are seeing that how a car in kinetic energy, which a car has a kinetic energy, and it smashes against the coil and it converts the kinetic energy into potential energy after contact. So that's why it's important to understand the scenario. So there is a car that is coming on a horizontal surface and there's a coil here. So this is scenario number 1, scene 1, and it was coming with a speed of 85 kilometers per hour. Make sure you're converting the units to meters per second. And this distance is not given, but you are talking about the distance with which it is compressing. And your job is to find K. So what is given to us? We have been given mass of the car, 1200 kgs, and speed V as 85 kilometers per hour. Go ahead and convert it. Once you convert it, you can substitute the values. I don't have the converted value right now ready, but you can go ahead and do the conversion as 85 instead of kilometers per hour. You can substitute for a meter. You want kilometer to go away, so it's in the denominator. You put 1000 meters here, and for time you want 1 hour to go away, and you put 1 hour is 60 minutes, but I will put 60 minutes into 60 seconds is 3600 seconds. Sorry, the space here is really constricted. 3600 seconds. Once you solve this, you should get a number for it. I don't have my calculator around and I don't want to spend time on that. You go ahead and solve that, but I'll show you the setup. So assume that this V is there. This is actually V naught, your initial velocity, and then the car comes to rest, so the final velocity must be 0. Okay, and the coil or the spring compresses by 2.2 meters. The x is given. This is not this distance. Do not think that 2.2 meters is this. it is the when it strikes a horizontal coiled spring and is brought to rest in a distance of 2.2 meters. What is the spring's constant? So it comes to rest. The car comes to rest because it gets compressed. So that distance is 2.2 meters. Okay, so it must be really big spring, and the car must be smashing it really hard with a high speed so that it compresses by so much. So we'll use the energy conservation principle, assuming that there is no friction or anything, because he's not told us about the non-conservative forces. So we'll assume that change in Ke plus change in potential energy, just like we did the gravitational potential energy problems, is equal to 0. Now we'll write down the change in kinetic energy as 1 by 2m v square minus 1 by 2m v naught square. Always solve these problems like this, whether there is a final velocity or not, but always set up with the right kind of equation first. 1 by 2 kx square, which is the final compressed state, minus 1 by 2k x naught squared, that is when it was not compressed. So when it is not compressed, obviously it's understood it's going to be 0. So again, my final velocity was 0 because the car comes to rest. The initial x naught is 0, so these two terms are gone. So we have basically 1 by 2 minus 1 by 2 mv naught squared equivalent to or minus plus 1 by 2 kx squared is equivalent to 0. So subtracting minus kx squared on both sides, so you will get 1 by 2 mv naught squared equivalent to minus 1 by 2 kx squared. So cancelling the minus sign, cancelling the 1 by 2, you work on these numbers. How about you get started with arranging this? One thing I would suggest you is that whenever we are doing these problems, you should do them simultaneously with me. Just don't look at the video only, do them as well, because you're anyways using this time. So your job is to find k, so rearrange the terms, divide this both sides by v naught x squared. So mv naught squared dividing both sides by x squared will give you k. Okay, so start substituting for v naught. I know by now you must have found the value for v naught in terms of meters per second. So you see that hour and hour is going, kilometer and kilometer is going. Your final answer is going to be 85 into 1000 over 36000 meters per second. So I will leave you to do that, and I can even it will be too much to substitute the whole thing in there, so you can do this calculation for v naught. And once you substitute the value of mass, you substitute the value of x as 2.2, square this, and definitely take a look at the brackets if you're getting the answer wrong. So your k after you're done solving should come out to be 1.4 into 10 to the power of 5 Newton per meter. So this must be a really strong spring. If you look at your chapter 6, there is a list of value of k given for different types of springs in a table, so you should take a look at it. All right, so next we'll talk about conservative and non-conservative forces. Basically, what does it mean? When work is done by a force, and some forces such as weight have special characteristics. A conservative force is one like the gravitational force for which work done by or against it depends only on the starting and the end points of the motion and not on the path taken. So we don't care really what is happening in between the path. So we ignore the path taken. That is a conservative force. When we can define a potential energy for any conservative force, just as we did for the gravitational force. For example, winding a toy, an egg timer, or an old-fashioned watch where you used to wind the screw to keep the time on track every day. You have to do work against its spring and store energy in it. So that spring unwinds by 24 hours, and after every 24 hours you have to rewind it so that the spring comes back to its original position. So do you see how even old-fashioned watches use the conservation of energy principle, where elastic potential energy of the winding spring, there's a spring inside, gives you actually measurement of time. Isn't that cool? And so what is basically non-conservative force? Forces like friction, air resistance, anything that you cannot retrieve and is dependent on the path taken. So for example, you're walking, and when you're walking, you are basically not going to be able to retrieve all the work you have done in walking those steps. So it's very hard to retrace back the steps and get the work back. A non-conservative force by definition is one for which work depends on the path taken. For example, I was saying friction is a good example of non-conservative forces. Work done against friction depends on the length of the path between the starting and ending points. It's very important. So if thermal energy, friction, for example, creates thermal energy that dissipates. If you're walking and if you're dragging a box, one of the losses can also be the work done. Thermal energy is lost. So removing energy from the system, there's no way I can get that thermal energy back. So those are all losses, loss of energy. In fighting against opposing forces is non-conservative force. I hope this is clear. This can be a multiple choice type of a question. And therefore, if I have non-conservative forces if there are non-conservative forces when the work is being done, then the equation, instead of writing it equivalent to 0, we write work done by non-conservative forces. Although I'm not going to give you non-conservative forces problem, we will always consider scenarios where there are no non-conservative forces. So you can directly write this as change in kinetic energy plus change in potential energy is equivalent to 0. That makes the work easier for you. If non-conservative forces were there, for example, force of friction, you'll have to find out the work done by the force of friction. For example, work done by friction. And that work done will be minus force of friction times the distance through which the friction happened, including the cosine of the angle between the force of friction and the distance. So then instead of writing WNC, you would write minus Fk, because force of friction is in the opposite direction of the motion. That's why we put a minus sign there. But I'm not going to give you problems with that scenario. Yours will be much simpler. So we will focus on conversion of Ke to Pe or Pe to Ke scenarios only. In the lab that I had given you, that's something that we are looking into. And for example, you will have scenarios if a rock is dropped on a spring, what will happen to this? So once it drops on the spring, you know it is going to get compressed by a certain distance, and that distance can be measured once we know the conversion. So the potential energy, gravitational potential energy of this ball is getting converted into elastic potential energy. Isn't that cool? So you can convert from Pe of G to Pe of elastic potential energy, and then you converted this into elastic potential energy. In the third step, the spring will not sit quietly. It comes back and throws this ball up in the air. So you are converting the elastic potential energy finally to kinetic energy. So you see conversion is happening in several steps here. So energy is only converted from one form to another, and so on and so forth. Important things about solving these problems. Again, I'm going to reiterate, some of you are not showing your entire work, and this was very clear in the exam. You just showed me, oh, okay, put the values 1.8 multiplied by blah blah blah, and then it is equivalent to 3.2. This does not make sense to me. I don't want this happening in the problem. Some of you are presenting your work excellently. Thank you for doing that and following the directions, but some of you do not understand. You don't show me the work, you don't get the points. So picturize this scenario, read first of all the problem carefully, picturize the scenario. Some of you didn't even show the free body diagrams. That was the most important part in chapter 4 and 5. So you just went ahead and solved the problem and gave me the answer. I don't care for the correct answer. I care for the conceptual understanding. So you have to show me the steps and determine the system for which energy will be conserved. So when you are reading these energy conservation problems, understand what is given. Is kinetic energy getting converted to PE of gravitation, or is it vice versa? Or is it PE of gravitation getting converted to PE of elastics? So understanding the problem. Or is it PE elastic getting converted to kinetic energy? So there can be different scenarios. So knowing what is happening in the problem is very important. Figure out what you're looking for and decide on the initial and final positions. Like, we will continue to use V as final, V naught as initial, X as final and X naught as initial, H as final and H naught as initial. You're free to use this as Y and Y naught as well. As long as you know what symbols mean, I really don't care whether you write X1 or X2 or X2 or X1. Your conceptual understanding should be strong. So to avoid confusion, I reiterate using the same symbols that you are used to. And choose a logical reference frame, apply the conservation of energy, and then go ahead and solve for these types of problems where you're using energy conservation. Your lab was based on this kind of scenario, where we showed that an object goes from higher end to a lower end, and its potential energy is getting converted to KE. PE is getting converted to KE, and then the KE helps it, because KE has velocity in it, that KE helps it go up again, so energy is getting converted. I also explained the example of a pendulum in the lab section. If you have seen the video, how an oscillating pendulum also obeys conservation of energy principle. At the highest points, PE is max. At the center, KE is max because it's speeding up towards the center. You should know the differences for multiple choice problems. So definitely read the chapter I would suggest read the chapter first, then come to my videos, and then solve the problems simultaneously while the chapter is going on. So the energy buckets on the right of the figure show how energy moves from all potential to all kinetic. The energy here was all potential, there was no motion. Once it dropped, midway, the kinetic energy and potential energy have equal values, but once it comes down on the floor, there is no PE. The entire energy is KE before it comes to rest. Okay, so there was a problem that I discussed in the online lab portion. We solved, there was a height given, and we solved for the speed at different positions. So go over that problem in the lab section. And then we can also solve problems based on if a bungee cord or some it bends, and you can there's an elasticity involved in here, so you can use the conservation of energy principle here. Please do not get confused by V1. V1 here is simply V naught, and X1 here is simply X naught, and V2 here is simply V, and X2 here is simply X, if I have to rewrite this equation, what is this equation and where did this come from? It is basically change in KE plus change in PE. I tell my students, just start with this. PE is equal to 0. And change in kinetic energy, 1 by 2 mv square, always final first, 1 by 2 mv naught square. The initial comes later. And since we are talking about elastic potential energy, I'll use 1 by 2 k x square for final minus 1 by 2 k x naught square is for the initial. So that's what it means. And if you take all they have said all the initial energy must be equal to final energy because there are no losses. We are talking about conservative forces. We are assuming there are no losses. Basically, that's what it means. All energy initial energy must be equal to all final energy. You can write it that way also, but I prefer writing the equation like this. When you write it in the form of change, then you can cancel whichever is 0. You will be left with 2 or 3 terms. So it's a good idea to work on one last problem before we sign out for today. And so there is a problem, a 0.100 kg toy car is propelled by a compressed spring. This problem is not there on the handout. This is one of the examples I'm using to explain how energy in a compressed spring can launch a toy car. So basically, if you have played with Hot Wheel track, or if you have played with toys where you're launching a car by pressing a button and the spring inside it launches a car, and it can go ahead and go around a loop in a Hot Wheel track as well. So the car follows a track that rises above the starting point. The spring is compressed. You have to do 2 things. You have to find how fast the car is going before it starts up the slope, and how fast is it going at the top of the slope. So the diagram is not there. I should have put the diagram, but I will draw the diagram for you so that you know that. So there's a spring over here and there's a toy car, and the car is going like this at the top. So you're launching it. Your job is to find if I use this path for it to go. So we have to find how fast the car is going before it starts to go up the slope. You have to find the speed here when it was launched. Okay, so that means it's the initial velocity, because when the spring was compressed and the car was attached here, somebody pressed the button and the car was launched. So that means we can find the initial velocity. And once it's launched up, it's getting converted. So the car reaches here. What your second part is, how fast is it going at the top of the slope. So it's a really good problem, and we can first list out what is given in the question here. Okay. So hang in a second, I'm trying to retrieve the given quantities. Using the principle of conservation, the roller coaster loses potential energy as it goes downhill. And right. So I'll give you some time to list out the quantities here. So how about you go ahead and start substituting the values. Okay, so if you have started gathering your work, I'll say change in kinetic energy plus I'll start with the conservation of energy is equivalent to 0, considering there are no non-conservative forces. Actual formula is given as WNC. When we cross it out, we say that it is equivalent to 0, but you can simply write 0. So there are three types of energies that are getting converted: the gravitational potential energy, the elastic potential energy, and the kinetic energy. So it has, how many things are there? There's initially it is at rest, right? And then it's going up, so there must be a height as well associated. So gravitational potential energy is not to be found here. We are not trying to find out, we're assuming that's not there. So we will use the elastic potential energy of the spring only. So 1/2 mv squared minus 1/2 mv naught squared plus the elastic potential energy of the spring, which is 1/2 kx squared minus 1/2 kx naught squared. So you could also write it all the initial quantities on one side and all the final quantities on other side. I can also write the initial, I can rearrange the terms, but for part A, he's asking you to find out initial height is 0, final height is also 0. So we have initial velocity is 0, and you have to find out what is happening to the final velocity. So if I write down this equation as 1/2 mv naught squared is gone. Okay, so when this is the position when it was over here. So basically this v represents what was the velocity here. So energy is stored in the elastic potential energy, and our equation is therefore this k of initial is there already, and once it is released, the kx square will be 0. Because when it is released, it comes back to its own position. So what are the quantities that I have? 1/2 mv squared, this is gone, and minus 1/2 kx squared, x naught squared is equivalent to 0. So your job is to find out the speed with which it is going to be released. So I have the right setting here. 1/2 mv squared is equal to 1/2 kx naught squared. 1/2 and 1/2 goes away, and we can find the v. V is divide both sides by m. You get, so far I have v squared. This is kx naught squared over m. Then take the square root of this. You'll get square root k times x naught over m. That is the mass of the toy car. And go ahead and solve these. So once you substitute the values, you should get the speed with which the car is launched. If you go back, we have mass m as 0.100. The car follows a track that rises 0.180 meters. We are not using this scenario yet because we are only trying to look what is happening over here. So the spring is going to launch the car. So we are not concerned with the height yet. Okay, so that will be the second part of the problem. When it reaches here, that is part B, we will determine what happens to the height. Okay, and the spring is compressed. So this is of our concern in the part A of the problem. 4, so you have 0.04 meters, and K is also given here. So you have X here. You have height, this is for part 2. And then you can go ahead, and he's also saying work done by friction is negligible. That is why WNC is equal to 0. So now we go back to our work. Now we know the numbers. You go ahead and find your V. So the once you substitute K, you substitute X, you substitute the mass, you should get 2.00 meters per second. I will pause for a little while for you to finish the work. Then I get to the part B. So what is the part B saying? First part was telling us to find out the speed with which it is launched, how fast the car is going before it starts up the slope. When it starts up the slope, potential energy due to gravity is 0. The entire conversion happens between PE elastic to kinetic energy. All right, now for part B, we'll see what is happening. So I have now, once it started moving, okay, once it was going up over here, supposing it started, the potential energy elastic is of no use now. That process is done. So no contribution from elastic potential energy. Now the scenario is simply between your kinetic energy and your potential energy. Okay. So we can also use the same scenario. We can say, okay, there are several different methods that you can use. You can use the contribution of the elastic potential energy. You can solve it in one step. 1/2 kx initial squared, because that's giving it the initial potential, must be equal to 1/2 mvf squared. This is, remember, this is for the part here. Okay, so forget what we did in part A. Now let us consider this part and this part. Forget the path in between. That's why we consider them non-conservative forces. We don't consider the path in between. We just consider the initial and final positions. So in the final, we should have our 1/2 mv final square, final, that is the velocity at the position 2. And what is the height over there at the part 2? mg h of final, which is also given. So you must be wondering, how did we get this equation? What is this meaning? Okay, let me elaborate on this. Let's again do change in kinetic energy plus change in potential energy equal to 0. Let's first write the equation. So change in kinetic energy between this point and this point when it was at rest. I don't care for part 1, for the part B. So the change in kinetic energy was 1/2 kx squared minus 1/2 kx naught squared. That's, sorry, the potential energy. Okay, so that was the PE, change in PE. It really doesn't matter which one you're writing first, but we have to also write down the gravitational potential energy. Okay, so the gravitational potential energy will be mgh minus mgh naught. Now, because we're considering this position to this position, so all the three energies have to be written, plus 1/2 mv final squared minus 1/2 m initial squared must be equal to 0. So this term is gone. This term is gone because finally the spring comes back to its position and the initial velocity was 0 when it was just prepping up. So you're left with three terms, 1/2 kx squared, mgh, and 1/2 mv squared. That is what we have also written here. So once you substitute all the values here and you work on the numbers here, you'll get an equation and you'll find out the final velocity Vf. How about you solve this on your own, set up all the terms, And when I send the PowerPoint, not the video presentation, because the video presentation ends here, so I want you to work on this problem. In the PowerPoint, I'll send you the solution as well. So VF is equivalent to, in the end, you should get VF as 0.687 meters per second. In part 1, you found that velocity of 2 meters per second with which it went all the way up, but at the top it's kind of slowing down, which is expected because now potential energy is higher than the kinetic energy. So this is your homework kind of thing for today. Go ahead and solve this problem from scratch. Understand potential energy in this problem has all the two types, that is elastic and gravitational. That is why I wanted you to see this problem. Okay, it is not part of your textbook, it's just an explanation. So other forms of energy and energy transformations, some things that we see that there are other forms of energy as electrical energy, nuclear energy, thermal energy, chemical energy, and so on, that we are not solving any problems related to them, but as long as you know that there are other energy sources. Work is done when energy is transferred from one object to another or from one form to another. Accounting for all forms of energy, we find that the total energy neither increases or decreases. Energy is, as a whole in the universe, is conserved. So you cannot isolate energy. So in the end, I just want you to know that this is part 2 of your class. Part 3 will be discussing on power. That will be a short lecture. Along with that, I will do the multiple choice for this chapter as well. All right, thank you.